Your body is an amazing thing. You can get scraped, cut, or worse. The human body has the ability to bounce right back. Other than a little scar tissue, you're as good as new. NASA is designing organic structural material that has that same ability. NASA's self-healing material is next on Real World. Imagine a military plane flying a dangerous mission. Just a bit of enemy fire could bring that mission down. Or think of a spacecraft exploring new worlds. A tiny bit of space debris could cause the crew to explore ways to stay alive instead of new frontiers. But what if there was a way to prevent punctures in airplanes and spacecraft? NASA's looking at a way not to prevent them, but to fix them immediately. By developing a self-healing material in a NASA lab, the agency is hoping to negate some of the biggest dangers of air and space travel.
The kind of self-healing material that we're looking at is puncture healing.
Mia Siochi is the acting head for the Advanced Materials and Processing Branch at NASA's Langley Research Center.
The way we test it is actually shoot a bullet through it. And what we're looking for is once the bullet penetrates, that it will close immediately right back behind it. What happens is the polymer inherently flows as the bullet penetrates. And the reason is, as the bullet goes in, it actually raises the temperature around the region where it goes in.
Polymers are substances made of many small molecules joined together to make long chains.
And in a NASA chemistry lab, they have come up with a polymer that will flow at the temperature the structure will be at as penetration occurs.
As the bullet penetrates, it pulls a little bit of the material with it, but then as it leaves, then the material will snap back. And when it snaps back, it actually seals.
This is pretty amazing stuff. It stands up to punctures and a whole lot more.
This is the result. You can see where the saw cut through, but the structural integrity remains intact.
We have looked at this material for like a fuel tank application, for example, where you shoot at it and there's liquid in a container, and it actually works. So it was gratifying to see that when we actually test this material on the field, you can see the bullet penetrating here, and the material pops out and then goes back in. We've done this from the side and also from the front. The camera is fast enough to pick up the bullet going through, and there's a shock wave that accompanies the healing of the material.
Similar material was already available. Used in golf balls and targets at shooting ranges, it had many of the qualities scientists were looking for, but not all of the qualities.
The material Cerulin is self-healing, but one of the properties that it doesn't have is that it's not structural load bearing.
Keith Gordon is a research materials engineer here at NASA Langley Research Center.
What we want to do is we want to make a material that has self-healing properties, but we want to increase upon the mechanical properties or the structural load-bearing properties.
So Keith and his colleagues set forth to make a material that could self-heal and have the structural integrity needed for NASA applications. They needed to develop a material that had more tensile strength than previous self-healing materials. Tensile strength is an important factor in determining a material's load-bearing ability. It is a measurement of the stress at which a material breaks or permanently deforms. Stress equals load divided by area. And that was just one of the qualities they had to account for.
That's part of the chemistry, all of the brainstorming in terms of the chemistry involved. We need a material that is easily processable. To make a polymer, you have to start with monomers, small molecules, in hopes to making a large molecule. And so what we have here is we have the monomers dissolving right now. We have another monomer that we're going to add that's going to initiate the reaction. What we hope to have after about 12 hours polymerization time is a polymer. What we're going to do from that point is isolate the polymer. So it's going to go from a liquid type of appearance now to a powder. We're going to take the polymer powder and then we're going to place it inside of a mold, press it, and we'll have our 3x3 panel.
The work in the lab has produced a product that will be beneficial for future space exploration.
In NASA applications, what we're looking at is space structures, for example, that self-heal habitats, for example. And so what we're interested in is that if there's an event where it gets hit with a micrometeoroid, you can retain the pressure in the habitat. And we've actually tested this material at close to micrometeoroid velocities, up to 5 kilometers per second, and it does close back up.
So work in the lab will continue, with the goal to make NASA's future space exploration as safe as it can be.